Hi everybody, welcome to these slides on hash tables. This closely follows a portion of the reading. We are reading the entire chapter on hash tables, and there's some pretty sophisticated math that's used to demonstrate the performance of the methods that we might build for a conventional hash table. And these lecture slides really cover open addressing, specifically linear probing, in which the length of the probe is just a step of one. And of course, in this domain of hash tables, there are different approaches. That is, there are different ways to probe. However, we're really looking at the simplest way to probe. And then as an alternative, and this is also introduced in the reading, we can implement separate chaining, in which we have a linked list at each spot in the underlying array. And when collisions occur, we simply add the key to the linked list at that spot in the array. And that approach, separate chaining, has its advantages. And it's really just based upon the requirements that we're able to discover which approach to implementing a hash table makes sense. So we have a hash insert method, and the pseudocode for that is illustrated here. Notice in the loop we have what translates to a do-while loop in Java because the test comes last. So we're guaranteed at least one iteration out of this loop. And at the top of each loop, we're calculating the step, we're calculating the key based upon the key and also the index. And you can see if the hash key that's calculated refers to a spot in the underlying array that's empty, we know we found the right place for the given key, in which case we can just return the subscript where the key is put in the hash table. And if we don't encounter a null at the hash key that's initially calculated, we're adding 1 to I, and we're recalculating the hash. So this actually simplifies things to a very large extent. The fact that we're calculating the hash key with each iteration of the loop. And we're looping until I is equal to m. And in the event that we reach I equal to m, and we haven't found a spot for the key, we can then surmise that the hash table is full, in which case we throw an exception, or this error, hash table overflow. And we also have a method for searching for a given key. We're providing the hash table and also the key to this hash search method. And we're looping again using what translates to a do-while loop in Java. And with each pass of the loop, we're calculating a new key, a new hash key. And if we encounter the key we're looking for, we're simply returning its subscript. And with each pass of this do-while loop, we're adding 1 to I, and we're looping until we encounter a null, or I is equal to m. And if we get through the loop without ever encountering the key, we're simply returning null. And that null value represents the fact that the provided key was not found in the hash table. And here you can see an implementation of insert in Java. And after you do the reading, this approach should make sense. It's actually fairly sophisticated what's going on. So it's important to try to get a handle on how this insert method actually works. you'll find this code as part of the lab that we're currently working on. This is the implementation of insert that I provided in the starter code. And you can see there's some similarities between this implementation and the pseudocode that we looked at on one of the previous slides. And what you can do to get a feel for the way this insert method works is to track it. That is, create a hash table and then perform an insert of a given key. And that should give you a feel for how this method actually works. We also have an implementation of find as well. And this is identical to the implementation of find that is given in as part of the starter code in the lab that we're currently working on. And this is actually fairly sophisticated what's going on. You can see we have a branch, we have an if, we have an else if, we have an else if, and we have an else. And the one thing to keep in mind about this implementation of find is we're making the assumption that an element that is set to -1 is empty and has never contained a key, and an element that's set to 0 has a key, has no key. However, it previously did have a key. And so this has some important ramifications for the way that we implement the delete method. And of course, implementing the delete method is part of the lab. And this is something that you all will be working on. And I also have some hints for the lab, Lab 4. You should take note of how the find method disclosed on the previous slide makes a distinction between the keys of -1 and 0. -1 is used to mark a cell that has never been occupied, and 0 indicates that the cell previously contained a key which was subsequently deleted. And if you keep these sentinel values in mind, it should be not too difficult to implement the delete method for the hash table.